In previous videos, we had talked about how to make alcohols, how to synthesize them, and most of our synthesis reactions involved reduction of more oxidized molecules like ketones, aldehydes, carboxylic acids. Now we're going to move into reactions that you can do with alcohols as the reagent. What can you turn alcohols into? And in this video, we're going to talk in general about a set of elimination and substitution reactions which are commonly done with alcohols. Now, the first elimination reactions that we're going to talk about are dehydration reactions. So we're going to lose water. That's what the dehydration means. And since these are elimination reactions, we're going to end up with an alkene product. Now, the first one that we're going to look at is how to dehydrate tertiary alcohols, and this is actually pretty familiar reaction to you. Should be. We talked about this really when we introduced an E1 reaction, and so we can draw a tertiary alcohol. Let's see if we can do that. And if you remember, when we were introducing the E1 reaction, we said, well, we can just add some strong acid like hydrochloric acid in order to protonate that alcohol, resulting in the conversion of the bad OH leaving group into a good water leaving group, right? This should be familiar to you. If it's not, look back at some old videos and notes about this. Now, we said this water could just leave, and this is a reasonable step in the reaction since we have a tertiary substrate. So the carbocation that we leave behind is pretty stable. Here's our dehydration. We've lost water as the leaving group, and then this chloride can act as a general base to finish an elimination reaction. Now, since we're doing an elimination here, we have to remember this is our alpha carbon, right, with the positive charge. I have 3 beta carbons, which are all similar to each other. And so it doesn't really matter which beta carbon in this example my base abstracts, right? I'm going to generate hydrochloric acid. The electrons will crash in here to form our final alkene product plus our hydrochloric acid. Okay, so this is a classic E1 reaction. The only step is that we have to take our alcohol, which is a bad leaving group, and protonate it with acid in order to make it a good leaving group. This only works on tertiary substrates, which give readily these tertiary carbocation intermediates. And really, we'll see when we talk about substitution reactions that this elimination reaction is going to be in competition with SM1. This chloride, instead of acting as a general base here to abstract a beta carbon hydrogen, could have just come in and quenched this carbocation through a substitution reaction. And we'll see that later in this video. Okay. Now, let's go on and talk about how do you dehydrate these alcohols if they are primary or secondary. And that's a little different, okay? While this reaction up here was an E1-based mechanism, our primary and secondary alcohols, that's not going to work because they're not going to make very stable carbocation intermediates. And so let's look at a primary alcohol here. Now the reagent we're going to use in this primary alcohol there's really two of them. One's a reagent POCl2, and so let me just write that out. POCl3. Got 3 chlorides on there. And we're going to do this in the presence of a solvent. The solvent being pyridine. And pyridine is a general weak base that looks like this. Okay, now our goal here is really the same. We're going to remove water somehow and result in an alkene product, but we can't do it through E1. We're going to have to do it through an E2 based mechanism. Now the problem with E2 again is that this is a bad leaving group, so we're going to use this POCl3 reagent in order to convert our alcohol into something that's a little better leaving group. Now how are these two molecules going to react together? Well, this P double bond O acts a lot like a C double bond O, like a carbonyl. And what I told you, and hopefully what you'll remember from this course, is whenever you see a carbonyl, you need to think of the carbon in it as having a partial positive charge. And that's true for this phosphorus here also. And so nucleophiles, like alcohol groups, can attack the partial positive charge on the phosphorus. These electrons can come out to form our light bulb. They can come back in to reform the carbonyl because we have a good leaving group here in chloride. Okay, so what this set of arrows results in is that we have formed a new bond between the oxygen and the phosphorus. We have lost one of our chlorides, but the others remain the same, right? And this phosphorus is probably going to have a pretty good partial positive charge. It's not only this oxygen that's ripping electron density away from it, but these 3 chlorides are also. So this is a pretty reactive molecule. This oxygen here is going to have a positive charge. And we've generated a chloride. Okay, now the next step in this reaction is that our pyridine is going to act as a general base to remove that hydrogen, which leaves us with this nice intermediate plus our pyridine that has been protonated and our chloride, right? Now this molecule here is a pretty good leaving group, and so now as we do a dehydration reaction, we can abstract a proton from the beta carbon here, and then that will kick out. This is a leaving group as we form our alkene. Now this proton has to be abstracted by a general base. It can be this chloride, or since pyridine is a solvent, we could have pyridine come in and remove another proton here. Turns out the pyridine is a little better base, but if you use the chloride here as your source of base, that's fine also. So just like a regular E2 reaction, in one step we're going to remove that proton, generate our double bond between the beta and the alpha carbon, and then have our leaving group leave. So our final product here is an alkene where we've generated a double bond between the alpha and the beta carbon. We've got our solvent, which has become protonated. Our leaving group from our original reagent. And we also generated a chloride as part of this. Okay, so if we look at this reaction, it's a pretty classic E2 reaction. The one twist is that we had to use our POCl3 reagent to generate this good leaving group so that our E2 reaction could happen all at once to generate our alkene product here.